Oh, psych. Actually, I wanted to do one more thing before we got to the analytic derivation, and that is I wanted to illustrate the progression of excitation k-space trajectory for a one-dimensional slice-selective excitation pulse specifically. Okay, so this is the kind of thing you would see if you opened up any MR pulse sequence that is 2D and slice-selective, and looked at its excitation RF and gradient waveform pair. Okay, so let's illustrate what is going on here, and specifically what we're going to do here is enlighten why we need this extra gradient lobe here on the end of the pulse. Okay, so here's our RF. This is the V1 of t. I'd prefer to use a different color there. Here's our gradient, right, our GZ of t. Now, before we defined kz of tau, comma t, capital T, as being equal to minus gamma times integral from tau to capital T of GZ of S ds. Okay? So we are now in a position to plot this bad boy, okay? So if we're looking like way back here in time, before the pulse even starts, right? So let's say we're right here. The total amount of area under the GZ waveform is going to be positive, right? Now then we get a minus sign here, so we integrate the area, then we get a minus sign, so this guy is going to be positive, and then it's going to go negative. So we're going to start out, before the pulse even starts, we're actually negative in excitation k-space, right? And so then once the pulse gets going, this positive area is going to cancel out less and less, right? We're progressing along here, so the total area remaining at any given time point in here is decreasing as time increases, right? Because it's canceling out less and less with this with the refocusing lobe. That part is called the refocusing lobe. So that means that the kz is increasing linearly in time, right? Until it gets to the point where we have only this refocusing lobe left over, right? And it's all negative, its area is negative, so then we are left at a positive kz at the end of the pulse. And then as we progress along that guy, then we go back to 0, it turns out, right? Because the integral of the remaining gradient goes to 0. Okay, so we can define two different time segments here. So we have the actual segment during which we have RF on, we'll call that time segment 1, and then we have the segment during the gradient during the refocusing lobe, and we'll call that segment 2. Okay? And just to clarify, I want to say explicitly that time capital T is right here. It's the end of the pulse, right? Hopefully you pick that up. So what is happening here is that as we're marching along in kz, the RF pulse is applying a weighting along k-space, right? So we started out negative in k-space, so at this point in time during the pulse, we were negative, then we moved positive, right, during time segment 1, and then at the end of the pulse, due to the refocusing lobe, we moved back to 0, right? So that was part 2 of the pulse, right? The refocusing gradient lobe. Okay, so the RF has applied a weighting in k-space during time segment 1, and then after that pulse, there's a linear phase ramp left over because we're at a positive kz location at the end of the RF, right? So sorry, that should say end of the RF. There's a linear phase ramp left over. And so what that means is that the signal is going to be dephased in the z direction, right? If there's a linear phase ramp across the z dimension, and we're going to integrate across that, we're going to get some attenuation in our signal, right? Because the phase will have been dispersed. Okay, so what the refocusing lobe does is it shifts, or time segment 2 does, is it shifts the k location back to the middle of kz space, which refocuses the slice, right? So if we were to ignore that refocusing lobe that we had on the previous plot, we would get less signal because we would have dephased our signal somewhat, actually. We would have remained at this positive kz location. Okay, so now we get to the analytic derivation of the small tip angle approximation. Okay, so here's our differential equation again, right, in the complex coordinates that I showed before. So it's d dt of the transverse magnetization plus I gamma g of t dot product with the location, right? Before, sorry, I was calling that r. So that means that this guy should really be, let's see, I should really make that r. So I'll call that r. And because I use r down there, and then I should use r here as well, sorry. Okay, that's good. Alright, so our differential equation is this, right? We've showed that before. So what we can do is multiply both sides by an integration factor, that is this guy, which we just kind of pull out of the blue conveniently. And so if we do that, we'll multiply both sides by that, and so here you can see we're just multiplying each term on the left hand side by this guy, right? So we're multiplying that by this guy, and then that by this guy to get this, and then the right hand side by this guy to get this. Okay? So now it turns out that the left hand side is a time derivative that we can write this way, right? So if you take the derivative of this quantity with respect to time, you would apply the chain rule, and so you'd get d dt of mxy times this guy left alone plus mxy left alone times the derivative of this guy, and then that would pull out the gamma gs dot r. Right, so we can combine those two terms on the left hand side as a single time derivative. Right, and so then that guy is equal to this. And so now we're in a position where we can integrate both sides over time, and we get the following. We get that mxy times this phase function is equal to I gamma m0 times the integral from minus infinity to t of the RF pulse times this other phase function, right, which we brought down from the right hand side there. And we can then multiply both sides by the complex conjugate of this term, right, to remove it from the left hand side and move it over to the right hand side, right? And we can then furthermore pull that complex exponential into the integral, right? It's not a function of tau, so we can pull it into the integral. And we can combine the two complex exponentials by adding their arguments, right? So you note here that the limits of integration here on these two terms, in the limits of integration, tau has to be less than t, right? So tau is only integrated up to time t, so it will always be less than or equal to t. Right? So that means that you see we have these opposite signs on these two complex exponentials, and so everything, and then because tau is less than t, we this whole segment minus infinity up to tau cancels out with the same segment on this side, right? So tau is less than t, so then that cancels out with everything from minus infinity to tau on this side in that term, and we're left over with only the difference, which is the integral from tau to time t of the gradient dot product with the location. Okay, and then this guy is then equal to k equal to this function here, where I should have a plus sign there. And then where k of tau comma t is equal to minus gamma times the integral from tau to little t of gs ds. So this is the same expression that we derived graphically, right? So we just showed how to derive this same result analytically. So again, we have this Fourier transform relationship between the magnetization and the RF pulse, that then we are taking the Fourier transform along the excitation k-space trajectory, which is defined here as the integral of the remainder of the gradient from the current point in time at which we knock down that little bit of magnetization. Right, so there's another mistake here that I just noticed, which is that this guy should be tau. And that's it right there. Thanks. Okay, so k of tau comma t has units of radians per length in practice, and it's usually centimeters that we use. So in our derivations, this is what we use. We use radians per length. It's often also specified in cycles per centimeter, which you get just by dividing 2 pi out of it. right? And then leaving the 2 pi in the complex exponential, multiplying k times x. So that's something to keep in mind. So it will either have units of radians per length, or it will have cycles per centimeter, and then you'll see another 2 pi in the exponential to transform the cycles to radians. Okay. So why do we care about the small tip angle approximation? Well, the linear Fourier relationship that it gives us is going to be very powerful, as you'll see, for designing and analyzing RF pulses. And so we'll see it in most of the pulse design problems that we look at, including the next topic for the next lecture. Thanks.